Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. Let's have level 1 on friction on wedges. The machine part ABC is supported by a frictionless hinge at B and a 10-degree wedge at C. Knowing that the coefficient of static friction is zero point 0.2 at both surfaces of the wedge, determine part A, the force P required to move the wedge to the left and the force P required to move the wedge to the right. So here is the given figure. First, let's have the free body diagram of the upper part of this structure. So we have for the solution N sub C, then friction, which is because P is required to move the wedge to the right, then friction should be down to the left, zero point 0.2 of N sub C. Then remember that the angle here is 10 degrees. N sub 0.2 N sub C makes 10 degrees with horizontal, and N sub C makes 10 degrees with vertical, as shown. So first, summation of moment about B. So let's have reactions at B. So N sub C, cosine of 10, the vertical component, times 250. Then minus 0.2 NC sine of 10 times 250, the vertical component of 0.2 N sub C. Then supposedly minus 600 times 200 or equal 600 times 200 mm. So from here, we can solve N sub C equal to 505.222 newtons. Next, let's draw the free body diagram of the wedge itself. So let's transmit the normal force N sub C and 0.2 of N sub C, which are now opposite to these directions. So down to the right and up to the right, 0.2 N sub C. Then we have normal reaction at D, and friction should be to the right, as shown. It opposes P. So first, ND, summation forces normal equals 0. Remember that NC makes 10 degrees with the vertical, zero point 0.2 NC 10 degrees with the horizontal. So ND plus 0 0.2 NC sine of 10 degrees equals or minus N sub C cosine of 10 degrees equals 0. So ND is equal to 0.95008 NC, and NC is 505.222. So 0.95008 times 505.222, ND equals 480.001 newtons. Then summation forces horizontal equals 0.2 NC cosine of 10 degrees plus plus NC sine of 10 degrees, horizontal component of NC, plus 0.2 ND minus P equals 0. So combining N sub C, 0.37061 N sub C plus 0.2 ND equals P. Substituting 0.37061 of quantity 505.222 plus 0.2 of 480.001 equals P. From here, we can solve for P. P is equal to 283.2 newtons. So, by the way, the first part is the force P required to move the wedge to the left. That's why frictional forces on this wedge would be opposing P. So, in the second part, the force P required to move the wedge to the right. So, friction forces should be to the left. This is now to the right, 0.2 of N sub C. So let's replace it with 0.2 N sub C, and it is to the right. So summation moment B equals 0. N sub C cosine of 10 degrees times 250 plus 0.2 N sub C sine 10, the vertical component, times 250, then equals 600 times 200. Solving for N sub C is equal to 470.802 newtons. Then we draw the free body diagram of the wedge again. This time, friction force 0.2 NC is going to the left, NC is still in the same direction. P is now going to the right as stated here. So point 2 NC, then point 2 NC down to the left, then ND, then friction to the left also point 2 of ND. So let's solve for ND. Summation forces vertical equals 0. ND minus point 2 NC sine of 10 minus NC cosine of 10. Vertical component of NC cosine 10 equals 0. Substitute the value of NC, which is 470.802. So ND is 1.01954 NC, or 1. So summation forces horizontal, P plus NC sine 10 equals zero point 0.2 NC cosine 10, the horizontal component of this, plus zero point 0.2 of ND. So NC P is equal to 0.0233134 of NC plus zero point 0.2 of 1.01954 of NC from here. So substituting, P is equal to 0.227227221 NC. So 0.227221 of 470.802. So P therefore is equal to 107.0 newtons rightward. Level 2, determine the smallest horizontal force P required to lift the 200 kilogram crate. The coefficient of static friction at all contacting surfaces is mu sub s equals 0.3. Neglect the mass of the wedge. So here is the given figure. Let's have the free body diagram of this crate, 200 kilogram crate for the solution. So weight, then the reaction here would be down to the left because the condition is we have the smallest horizontal force P required to lift the 200 kilogram crate. So if movement of the 200 kilogram crate is impending upward, so friction is downward. So therefore reaction should be down to the left at an angle of P sub S. P sub S is arctan of 0.3 and it is 16.699 degrees. So that's why R1 makes an angle of 16.699 degrees with horizontal. Then the effect of P is to push this to the right. So the reaction here is up to the right as shown. And the angle that R2 makes with the vertical is also 16.699. So let's have the force triangle of these three forces which are in equilibrium. So weight 200 kilograms times 9.81 followed by R2, which makes an angle with a vertical of 16.699 degrees. Then this is R1, which makes an angle with a horizontal of 16.699, horizontal plus vertical 90. So 16.699 plus 90, 106.699 degrees. Therefore, this remaining angle is 180 minus 106.699 degrees minus 16.699 degrees. So using your calculator, it is 56.602 degrees. We then apply the law of sines to solve for R2 and transmit R2 to the wedge later. So R2 as to sine of 106.699 degrees equals 1962 as to sine of 56.602. So R sub 2 is equal to 2250.966 newtons. Then we have the free body diagram of the wedge. Then that's P. Let's transmit R2, which is down to the left with magnitude of 2250.966, an angle with a vertical of 16.699 degrees. And we have here the normal to the underside of the wedge, which makes an angle of 15 degrees, the normal and the vertical 15 degrees, and R3 should be here opposing P. So that's 15 degrees. This is R3, and R3 makes an angle with a normal of 16.699 degrees. So we draw force triangle for these forces here. And we have P, then R3. R3 makes an angle with the vertical of 15 degrees plus 16.699. Therefore, the angle it makes with the horizontal is 90 degrees minus 15 degrees minus 16.699 degrees, and that is 58.301 degrees. Then this is R2 to 50.966. So it makes an angle of 16.699 degrees with the vertical. So with the horizontal, 90 minus 16.699 degrees, and that is 73.301 degrees. Therefore, this remaining angle is 180 minus 73.301 degrees minus 58.301 degrees. Using your calculator there, 48.398 degrees. Finally, by sine law to solve for P as to sine of 48.398 degrees equals 250.966 as to sine of 58.301 degrees. So P can now be solved. P is equal to 1978 newtons. Level 3. Determine the range of P for which the system of two blocks will be in equilibrium. Friction is negligible except for the surface under block B. So here is the given figure. For the first analysis, let's draw the FBD of the 120-pound force. Then let's analyze the normal reactions and with A. Then solve for P later. Take note only under block B where there is friction. For the second part, we analyze that there's no movement or slippage on this junction, and so we analyze P for the second part, and we have only friction under block B. So for the solution for the first part, we have the weight 120 pounds, normal reaction here, which makes an angle of 30 degrees with the vertical, and normal reaction here, which is horizontal because there's no friction on the upper block, only under block B. So therefore, summation forces normal equals vertical equals 0, and AB cosine 30 minus 120 equals 0. So NAB is equal to 80 square root of 3 pounds. Summation forces horizontal, 80 square root of 3 times sine of 30 degrees minus NA equals 0. So that means NA is 40 square root of 3 pounds. Then let's draw the free body diagram of the lower wedge B. Then transmit the reactions. We have only NAB, which is 80 square root of 3 pounds perpendicular to this inclined surface. Then at B we have normal, that's 30 degrees. We have, let's just have RB directly. This is P sub S, which is inverse tangent of 0.2. So the other possibility of RB would be here when we have minimum P. And this angle is also P sub S. So summation forces vertical equals 0. So tangent P sub S equals 0.2. So P sub S is 11.31 degrees. So summation forces vertical equals 0. Let's solve for P minimum first. So RB cosine of P sub S 11.31 degrees minus 80 square root of 3 cosine of 30 degrees equals 0. So R sub B is 122.376 pounds. Then summation forces horizontal, P minimum plus RB 122.376 sine of P sub S minus 80 square root of 3 sine of 30 degrees equals 0. So P minimum is equal to 45.28 pounds. Then P max minus 122.376 sine of 11.31 for this situation here. And minus 80 square root of 3 sine 30 equals 0. P max equals 93.28 pounds. So for the second analysis, we treat these two bodies as one, and there's no slippage along this plane. So take note that we have solved NA earlier for t square root of 3. Then we have the weight 120 pounds, here 80 pounds. Then normal reaction at under underside of B. Then friction, which is uh, either to the left or to the right. So for minimum friction, for minimum P, it is to the right. So NB equals 80 plus 120, so 200 pounds. Then summation forces horizontal, P minimum plus zero point 0.2 of NB, 200 minus NA, which is 40 square root of 3 equals 0. So P minimum equals 29.28 pounds, which is lesser than 45.28. So this controls because we have the lower value here, P minimum. So this is the minimum P required for the system to have impending motion. Then for P max, 0.2 NB should be to the left. Summation versus horizontal, P max minus 0.2 of NB, which is 200 minus NA 40 square root of 3 equals 0. So P max is 109.3 pounds, which is also greater than this. So therefore, the range of values of P for which the system of two blocks will be in equilibrium would be 29.28 pounds less than equal to P, and P is less than equal to 109.3 pounds. So that's it for this problem. Level 4. In wood frame construction, two shims are frequently used to fill the gap between the framing S and the thinner window or door jamb D. The members S and D are shown in cross-section in the figure for the 3-degree shims shown. For the 3 degrees shim shown, determine the minimum necessary coefficient of static friction necessary so that the shims will remain in place. So here is the given figure. Let's have the solution and the free body diagram of the left shim. Then let's have the angle here, which is 3 degrees. Let's call that theta in general. Then the normal to these surfaces and the line of action of the resulting reaction with friction. So let's call the reaction at the left as R1, the right R2. And for the other possibility, depending on the movement of the wedge, so here is also the other possibility. So this angle here is between the normal and the line of action of the reaction. Resultant reaction, friction plus normal, is P sub S. And we have the normal axis, and this is the normal line to this plane or surface, and this is the line of action of another resultant force, friction and normal force. So the angle between normal and this line of action is also P sub S. Then the angle that between the normal and the horizontal is theta, as shown. So therefore this is P sub S minus theta, that this angle here, P sub S minus theta, which is supposedly equal to this angle here, because these two have common horizontal line and common red line. So this is also P sub S minus theta. Therefore, the total angle here is 2 times P sub S minus theta, which is also the total angle here. 2 times P sub S minus theta. So therefore, this angle, so that it will be 2P sub S minus theta, should be P sub S minus theta. So this is also P sub S minus theta, so that P sub S minus theta plus P sub S is equal to 2 theta S minus theta. So the red lines, R1 equals R2 for no slip condition. So remember the reaction at the left red line along these red lines here is R1, and it opposes on the other red lines here, R2, for no slip condition. Of course, from the principle of two-force body, the forces should be equal and opposite to each other for no slip condition or for equilibrium condition. So take note, red lines are lines of action of R1 and R2 for no slip conditions and serve as range of R1 equals R2 for no slip or equilibrium condition. So as I said, in the left portion, R1 should be within this range, these red lines here, for no slip condition. In the same manner, on the right side, this is the range of R2 so that the shim, 3-degree shim, will not slip. So the wedge is self-locking if slippage occurs only in one surface and there's no slippage on the other. Or so that's it, because even if one surface is about to slip, the other will not, the shim or the wedge will remain in equilibrium. So therefore, for self-locking case, 2P sub S minus theta should be greater or equal to 0, or the reaction should be within this range for self-locking wedge, or so that this wedge cannot move or this shim cannot move. So theta is 3 degrees in the figure given in the problem. So 2P sub S minus 3 degrees greater than equal to 0. So P sub S should be greater equal to 1.5 degrees. Therefore, since P sub S or mu sub S is tangent to P sub S, so mu sub S equals tangent of P sub S should be greater equal to tangent of 1.5 degrees. So from here, we can now solve the minimum coefficient of static friction mu sub S. So it should be greater or equal to 0.02619. Level 5, two 8-degree wedges of negligible weight are used to move and position the 800 kilogram block. Knowing that the coefficient of static friction is 0.3 at all surfaces of contact, determine the smallest force speed that should be applied as shown to one of the wedges. So here is the given figure. For the solution, let's have the free body diagram of the 8-degree wedge. So let's call R1 and R2 for the resisting forces on that wedge. So R1, which makes an angle with the normal to the surface with P sub S, and the normal and the horizontal makes an angle of 8 degrees, the angle of this wedge. R2, because the normal is horizontal, makes an angle with horizontal of P sub S only, where P sub S is inverse tangent of 0.3. So P sub S is equal to 16.699 degrees. So therefore, if we draw the first triangle, we have P downward, then R1 makes an angle of 8 degrees plus 16.699 degrees with the horizontal. So with the vertical, 90 degrees minus 8 degrees minus 16.699 degrees, that would be 65.301 degrees. Then we have R2 here, which makes an angle with the horizontal of P sub S, 16.699. So with the vertical, 90 minus 16.699 degrees, and that is 73.301 degrees. This remaining angle of the triangle is 180 degrees minus 73.301 degrees minus 65.301 degrees. So using your calculator, we have 41.392 degrees. Using sine law And let's express R2 in terms of P. We need R2 because we transmit R to the 800 kilogram block later. So R2 as to sine of 65.301 degrees equals P as to sine of 41.398 degrees. So expressing R2 in terms of P, R2 is 1.3739 P. Then we draw the free body diagram. We transmit R2 to the 800 kilogram block. So for the free body diagram, we have the weight 800 times 9.81, then R2, which is 1.3739 P, down to the opposite to this, down to the right, with an angle with horizontal of 16.699 degrees. Then for the normal of the bottom of the block, the reaction should be up to the left, and which makes an angle of P sub S again with the vertical, because the vertical is the normal to the surface, and this is 16.699 degrees. So let's draw the free body diagram, or the first triangle of these three forces. 800 times 9.81 is 7848. Then we have 1.3739 P, then R3 shown. So R3 makes an angle of 16.699 degrees with the vertical. So 1.3739 P makes an angle of 16.699 degrees with the horizontal plus 90. So this is 106.699 degrees. This remaining angle opposite to 7848 newtons is 180 degrees minus 106.699 degrees minus 16.699 degrees. And that is equal to 56.602 degrees. Finally, by sine law, 1.3739 P as to sine of 16.699 degrees equals 7848 as to sine of 56.602 degrees. Solving for P, P is 1966 newtons. So that's it for this first batch of problems on friction on wedges. And I hope that the explanations are clear and you were able to follow the solutions, and you will gain techniques on how to analyze wedges.